I built Ray Wilson's noise toaster from his Analog Synthesizers book about 10 years ago. It was a great way to learn a bunch of new skills and was a lot of fun to play with. I took it to work and the response was encouraging. Motivated by this success, I then chose to build a much larger synthesizer. Not because it was easy, but because I thought it would be easy. It took me 5 years. 3 more years and who knows, maybe I could have landed on the moon. It's time now for a new project. I'm going to build the Enigma Machine. To pull this off, I'll need to develop skills I don't yet have, and buy tools I don't yet own. It's perfect. My machining skills are as green as a freshly mown lawn. But hey, at least this way, there's plenty of room for growth. I live in a small country town in regional New South Wales. As a result, most of my money goes towards luxuries like food, shelter, and fuel. So the prospect of buying a real Enigma machine is next to impossible. They're rare and expensive. Really expensive. So I'll need to make my own. How hard could it be? Thankfully, I didn't have to start entirely from scratch. I found a set of blueprints created in 2003 by a team of German university students. With no experience manufacturing parts overseas, I outsourced everything to the lowest bidder. I got what I paid for. I'd found a great way to convert money into scrap, a kind of reverse recycling process. The worst part was that I'd made too many of everything. So who was to blame? Well, the blueprints were far from perfect. But the blame was all mine. I had no idea what I was doing. To make this happen, I'll need to make the parts myself. Using the university blueprints as my starting point, I spent the next year building a new CAD model based on thousands of reference photos I'd collected. It's a complex machine, so I've split it into 9 major pieces. The base, the lever, the plug board, keyboard, the lamp holder, the switches, the battery box and electronics, the rack, and the outer casing. The Enigma machine also came in an oak transport case, but that's a project for another time. For the next few videos at least, I'm going to focus on building this bit, the rack assembly. With over 1,000 parts, it'll be a good way to improve my machining skills. Or lose my mind. Hopefully in that order. Here are the parts I'll need to make to complete the rack assembly. The entry wheel, the rotors, 3 of them, the reflector, and a bunch of levers and other bits. I'll make most of these parts myself, except for the springs and screws, which I'll leave to the pros. The pins and bearings will be brass, with the remaining parts made from stainless steel, aluminium, and plastic. Before machining any parts though, I've 3D printed some placeholders, which should help me demonstrate how the pieces fit together. This is the plastic rotor core, which will need both the lathe and the milling machine. These are the 8 plate and pin retainers, which I'll make on the rotary table. These thumb wheels will be made of aluminium and will be a piece of cake on the CNC. But I think it could be more fun to make by hand. Let me know what you think in the comments. These small rotor bushings will be made from brass, and are held together with threaded inserts. I'll need to fit 26 wires in between these two parts, so it's going to be a tight fit. Here's the kerf ring with spacer. They'll be made from aluminium too. I know threading 3D printed plastic isn't a great long-term solution. It'll be fine, I promise. I'll need to use a 4th axis on the CNC to do the embossed lettering on these digit rings. The kerf rings are then attached to the digit rings, completing the assemblies. See, I told you it will be fine. This thin brass casing then fits inside of the digit ring. I have no idea how I'm going to make this part. Maybe something on the mill. And then I just force these two assemblies together. Well, I guess that's never coming apart again. There's a bunch of pins and springs here too, all of which are held in place with one of the pin retainer plates. Here's the entry wheel, which connects the rack electrically to the rest of the machine. The entry wheel is a lot more straightforward. If I can make a working set of rotors, I should be able to make this part with my eyes closed. But I'll still wear my safety glasses, just in case. I can then attach both rack ends to the base plate with countersunk screws. The rotors can now be placed in the rack. There's quite a bit of flex in this setup, given the supports are made from plastic. If you're wondering why I don't just 3D print the whole machine, this is why. I'm going to build a machine from the inside out. So I'll start with the rotor shaft. Here's the plan. Being my first part, it's pretty straightforward. About 90mm long, with a small feature on both ends. The brass bearings from the rotors run on this shaft, so I'm also providing some generous tolerance for a free running fit. I'm making the rotor shaft out of 316 stainless steel. That's easy to machine, right? Over to the lathe, and I'll start by securing the stock in the 3-jaw chuck. There's quite a bit of stick out, so I'll need some support, both physically and emotionally. Using a center drill to make a small hole at the end, and then swapping out the drill chuck for the live center. Cutting stainless steel, especially on such a narrow part, generates a lot of heat. So I'm being very generous with the cutting oil. I'm also being very conservative with this roughing insert. Now that I've got a consistent diameter across the length of the stock, I can be a little bit more aggressive. It's time to do something about this mess though. The damage on the casting was the result of a previous parting operation gone wrong. I can fix this by covering it up, which should also make future chip cleanup easier. Time to add some layout lines to check that I've got enough material to make the final part, which I then instantly remove without checking. After a few more passes, I'm closing in on the final dimension, so I switch to a finishing tool. And reduce the feed rate to improve my surface finish. These passes take about 8 minutes in real time. I'm saving those for the director's cut DVD. One final scratch pass, and the main shaft is complete. Switching out for the parting blade, I attempt to unsuccessfully remove the fillet left over from the turning tool radius. I've since purchased some super sharp, high-speed steel turning tools, which I'll try out next time. Looking at this footage, I'm not at all convinced the tool post has been tightened. Nonetheless, the stock is free, and I've got a first look at the rough part. It's time to work on the end features, so I'm swapping out the 3-jaw for the ER32 collar chuck. I'll work on this end first, taking the feature to its final length. I should have used a tool with a bigger radius for this facing operation, but I get away with it this time. I then do a few more passes at 0.25mm. And a final facing cut on the inside shoulder. It's probably time I replace that insert too. This feature is finished with a high-speed 2000 grit sandpaper WD-40 polish. It's time to bring the part to its final length. I'm about 13mm over size, which gave me plenty of wiggle room for the live center and parting operations. This time at the correct speed, with the correct tool, and then, after a few more passes, our turning operations are complete. Some delicate filing breaks the edges. And a final polish with 4000 grit sandpaper. You know what they say, if you can't make it good, at least make it look good. That's one part down, a couple thousand to go. Join me next time when I make this part, the rotor shaft holder. Thanks for watching. If you're not familiar with how the Enigma machine works, I recommend checking out Jared Owen's video. I'll leave a link in the description.